So let's talk about a technology that isn't just an upgrade to our current computers. It's a machine that plays by a completely different set of rules. I'm talking about quantum computing. It's a way of handling information that taps directly into the weird, wonderful, and incredibly powerful laws of quantum physics. Let's dig into what that actually means. But first, let me ask you this. Are the computers that run basically our entire world hitting a wall? I mean, for decades, they've just gotten faster and more powerful at this unbelievable rate. But what happens when that incredible progress finally starts to grind to a halt?
To really get why we need this quantum leap, we first have to understand the wall that classical computing is slamming into. And that wall, it's built from the very foundation of all modern tech, those simple little binary digits, the humble zeros and ones.
For more than half a century, the engine driving all of this progress has been Moore's Law. You've probably heard of it. It's the observation that the number of transistors we can cram onto a chip doubles roughly every 2 years. This is what's given us everything from the smartphone in your pocket to globe-spanning supercomputers. But that reliable trend, that engine of progress, is seriously slowing down. It's running out of road. And here's exactly why we're hitting that wall. For one, we're getting down to the atomic scale. Our transistors are becoming so tiny that the rules of classical physics just start to get fuzzy. We're also generating so much heat we literally can't get rid of it fast enough. And on top of all that, there are certain problems. I'm talking about things like designing new medicines or cracking modern encryption that are just so monstrously complex that even the fastest supercomputer on Earth would take thousands of years to solve. We are, quite simply, running out of physical space and classical tricks. So what do you do when the old rules stop working? Well, you find new ones. And that brings us to this new quantum paradigm. See, instead of fighting against the weirdness that happens at the atomic scale, quantum computing leans into it. It embraces it. It's a whole new method built not on clever engineering tricks, but on the fundamental laws of the universe itself. This is so important to understand. This is not just a faster chip. It is a completely different way of thinking about computation. It uses laws of physics that are, as one source puts it, completely dissimilar to anything powering your laptop or your phone right now. We're talking about a massive shift from just doing calculations to performing a kind of computation that actually mirrors nature. Now, this idea didn't just pop up overnight. It's been building for decades. The brilliant physicist Richard Feynman first floated the concept way back in the 80s. From there, we went from really basic machines at the turn of the century to systems with thousands of quantum bits, or qubits, just a few years ago. And then, in 2019, we hit a huge milestone. Google claimed it had achieved quantum advantage, solving a problem that was, for all practical purposes, impossible for any classical computer. So what's the secret sauce here? What is it that makes these machines so fundamentally different? Well, it all comes down to the basic unit of information. To get it, we have to move beyond the classical bit and get to know the qubit. Okay, think about it like this. A classical bit, the kind in your computer, is like a simple light switch. It's either on or it's off, a 1 or a 0. That's it, end of story. But a quantum bit, a qubit, is not a light switch. It's more like a sphere, representing this huge, rich space of possibilities. It's not just on or off. It can be a combination of both at the same time. And this sphere actually has a name. It's called the Bloch sphere. You can think of it as a map of a single qubit state. So the North Pole could be 1, the South Pole could be 0, but a qubit can exist at any point on the entire surface of that sphere. It holds an exponentially larger amount of information than a simple on-off switch because it represents the probability of being a 0 or a 1. Let's just break this down side by side. A classical bit, it has a definite state. It's either a 0 or a 1. A qubit, on the other hand, exists in what's called a superposition of both states at once. And here's the kicker. When you measure a classical bit, you get a definite answer. But when you measure a qubit, it's probabilistic. It suddenly collapses from that whole sphere of possibilities into a single, classical 0 or 1. Okay, so this ability to be in multiple states at once, that's just one of 2 quantum superpowers that give these computers their mind-boggling potential. Let's look at these almost magical properties, superposition, and something even weirder called entanglement. So first up is superposition. We already know this lets a single qubit hold way more information than a simple 0 or 1. But the real magic happens when you have a bunch of them. By being in this combination of states, just a handful of qubits can explore a massive number of possibilities all at once. That's where quantum computers get their insane parallel processing power. How do you even wrap your head around that? Well, luckily, the source material gives us a fantastic analogy. Think of a spinning coin.
While it's spinning in the air, what is it? It's not heads, and it's not tails. It's kind of both. It's a blur of probabilities. It's only when it lands, the moment we measure it, that it collapses into one definite state. That spinning coin, that's a great way to think about a qubit in superposition.
All right, the second superpower is even more mind-bending. It's called entanglement. This is where two or more qubits get linked together in this incredibly profound way, where they basically act like a single object. If you measure the state of one of them, you instantly know the state of the other one, even if they're on opposite sides of the galaxy.
This connection was so bizarre, so counterintuitive, that Albert Einstein himself famously called it spooky action at a distance. He really wasn't a fan of the idea. But it turns out this spooky property is very real, and it's absolutely essential for networking qubits together to perform calculations that classical computers couldn't even dream of.
So, we've got these incredible new tools with these spooky superpowers. What are we going to do with them? And what's stopping us from having a quantum computer on our desk by tomorrow? Let's get into the practical side of things, the amazing promise, and the very real problems. So what can we actually do with all this power? Well, because quantum computers play by the rules of the quantum world, they're perfect for simulating it. This could mean designing life-saving drugs by modeling molecules perfectly, creating revolutionary new materials, or even supercharging AI. But there's a flip side to that coin. A powerful quantum computer could also break most of the encryption that protects all of our data today.
To really get a sense of the raw power we're talking about, I want you to just focus on this one number, 200 seconds. That's it, a little over 3 minutes. Got it? Keep that number in your head.
Remember that 200 seconds? That's how long it took Google's quantum machine to do a very specific, very complex calculation back in 2019. Now, how long would that same task have taken the world's most powerful classical supercomputer? An estimated 10,000 years. That's not just an improvement. That is a different reality of what's possible. So, if they're so powerful, why aren't they everywhere? Well, just take a look at this. This isn't a computer case. It looks more like some kind of crazy, futuristic chandelier. And that caption says it all. A fragile state. The very superpowers that make qubits so powerful, superposition and entanglement, are unbelievably delicate. The slightest little disturbance from the outside world can make the whole thing fall apart. And that leads to some huge hurdles we have to overcome. The number one enemy is something called decoherence. That's basically when a qubit loses its quantum magic because of the tiniest bit of heat or vibration. To stop this, these machines have to be kept in these crazy isolated chambers, chilled to temperatures colder than deep space. And even then, errors creep in, and figuring out how to fix those errors without actually looking at the qubits, which would destroy the whole calculation, is one of the biggest challenges in all of science right now. Look, we are standing at the very beginning of a new computing revolution, one that promises to solve some of humanity's biggest, most complex problems. The challenges are massive, for sure, but the progress is real, and it's speeding up. This tech has the potential to change literally everything from medicine and finance to security. So the final question really isn't if it's going to happen, but when it does, are we going to be ready for it?